Hello everyone and welcome to the presentation of our paper Camera-based barcode localization and decoding in real-world applications. My name is Robert and for the next 20 minutes I will explain to you how we use the modern approach of deep learning and some classical approaches to manage the localization and decoding of barcode labels. Barcodes, as to see in this image, represents data by varying the width and spacing of the parallel lines. Due to different types of barcodes, they can encode numbers, letters, or even a full ASCII character set. The history of barcodes as good identification goes back in the 1970s, and since then they became worldwide acceptance due to safe handling and low-cost production. So, how can you read a barcode? Well, probably anyone saw already a handheld laser scanner like when he does his daily shopping. A barcode laser scanner is a closed form of light source and light receptor. The precondition to be able to read the barcode is that the scan line needs to be aligned to the barcode. And while the scanner needs to be mostly connected to some processing devices as a PC or an electronic point of sale. However, in the recent years, off-the-shelf cameras have become very popular and cheap. Nowadays, almost everyone is carrying a high-resolution camera in his pocket, which is a part of a smartphone. There are countless barcodes reading applications from mobile devices, which base mostly on one of the libraries listed here. In our project, we also use the zebra crossing library. To be able to decode the barcode information from a camera image, the image of the barcode must be large, without much noise and well exposed. And the alignment of the camera during the recording remains a precondition. But what if the barcodes, or better say, some goods with barcode labels, only pass the camera which is stationary? Then, as the example image shows, we get a few challenges when it goes to decoding the barcodes. We can have multiple barcodes in one image with various orientations. Some occlusion can happen. The barcode labels can be at different distances to the camera, so the scales differs, and the image at all can have some degradation as be blurry or under or overexposed. That this situation is not an imaginary one, let me show to you our problem statement. This paper is a part of the Smart Air Cargo Trailer project, which should optimize the short distances transport process at the airport, and our camera-based barcode recognition system is a central component of it. We detect the barcode during the loading and unloading of the goods from a truck. Here are a few key points about our setup. We have 5 industrial cameras with a resolution of 12.4 megapixels each. We cover our observation volume of 2.5 cubic meters and scans 4 sides of the load, means front, top, the left and the right side. Because the goods are transported on pallets with a forklift, we need to care about motion blur. And last but very important, we need to provide the information about the barcode passing through as fast as possible. So let us jump to the related work. Now, barcode localization has been a topic of several publications. For example, Gallo and Manducci restricted the localization problems to horizontal alignment barcodes. Having such an input, the localization can be achieved analyzing the horizontal and vertical derivatives of the image. However, this method is not very fast and doesn't work at all by barcode rotation over 45 degrees. Suros and Furmeyer presented some methods for rotation-independent localization. For a given input, they build edge and corner maps, and by a linear combination of them, they retrieve 2 silencing maps which indicate the barcode's area. However, this approach doesn't work properly if the image is blurry. Croissant and Munavar presented an approach called parallel segment detector. With this approach, they were able to segregate the barcode stripes even from bad conditioned images. However, the underlying line segment detector, which calculates a level line field for every pixel, is very time-consuming, making the whole approach not real-time capable. For about a decade now, neural networks have been successfully used for localizing the barcodes. Zamberetti et al. Proposed an angle-invariant method for barcode detection based on Hough transformation and a single and multi-layer perceptron. Since Hough transformation is an integral part of the algorithm, the barcode must be very present in the image, and the approach is time-consuming. Hansen et al. Introduced a barcode detection approach based on the You Only Look Once, short YOLO, detector, which provides axis-oriented bounding boxes that describe the location of the detected object. They also provide angle prediction for the detected barcode, but limited the localization to the axis-oriented bounding box. We actually take this idea of YOLO as a detector, but we found a completely segmentation of the barcode. Zarkov and Segainov presented a semantic segmentation network which provides a segmentation map for superpixels. This approach shows good results for input with good visible barcodes. However, the size of the network inputs has been set to 512 squares, which means that the runtime for larger input images, like this one we are dealing with, is likely to be significantly high. Let's go to image restoration. In general, a blurry real image, let's call it E, can be described as the convolution between the clear representation of an object, let's call it F, and a degradation function H. And like in a real scenario, we need to add some noise, let's call it N. So the inverse process given a blurred image and obtaining a non-blurred one is known as deconvolution. Well, if the degradation function is unknown, that's a blind deconvolution. The degradation function can be, for example, be estimated by analyzing the spectrum, as for example by Bruce et al. But however, this approach can only handle linear movement degradation. Chamalet et al. Presented an iterative barcode deblurring approach based on the bimodal characteristic of the barcode image histograms. Based on this observation, they were able to estimate the degradation function. This technique shows good results in the typical motion blur cases, but struggles by images with varying illumination or high noise level. Another approach presented Gallo et al., which based on deformable templates representing barcode symbols. The algorithm show good results if the barcode is well presented in the image. However, for small resolution, like when the barcode is far away from the camera, this solution is not working at all. For more than a decade now, machine learning has become important in image restoration too. These images are taken from the Deblurring version 2 publication and are part of the comparison of different deep learning algorithms for image deblurring. On the left, we see the blurred input image followed by 4 deblurring results. We see that these approaches are deblurring the input, but these algorithms do not necessarily try to bring out the sharp edges that we need for barcodes. For the best of our knowledge, there are no deep learning-based approaches which handle the deblurring of 1D barcodes. Our decoding pipeline can be subdivided into 4 modules, which are localization, segmentation, and contour estimation, orientation estimation and contour refinement, and finally decoding with optional deblurring. For the localization, we use the YOLO detector, and this in version 3 with the tiny one. The tiny version with the network input size of 416 squared allows us a fast processing of the total number of 5 camera images. With the original size of the images of 12.4 megapixel, we can only expect a rough localization of the barcodes. As you can see in this picture, the YOLO bounding box, denoted in red, does not always cover the whole barcode. Therefore, we always increase the size of the YOLO bounding box by about 13%. For the final segmentation of the barcode, we use the unit architecture, which is a typical model for these problems. We have modified the original architecture so it works with grayscale input images and have reduced the number of filters by a factor of 8. This results in a huge performance increase, but that does not reduce the accuracy that much. As input for a unit, we use non-uniform scaled patches based on the extended YOLO bounding boxes. The scaling to images size of 256 squared makes the barcodes more or less uniform in size, and the execution time of the algorithm is constant. The segmented barcode area can be seen as a white blob in the third picture. For this region, we first calculate the contour, denoted in red, and then a polygon approximation, which is shown in the last image with the green annotation. As maximum distance between the line and the point, we have chosen 10 pixels, simply by assuming that the barcode with a height of less than 10 pixels would not be solvable anyway. So in the next step, we want to determine the orientation of the barcode, which is based on the observation that there is an orientation of the barcode with respect to the edges of the polygonal approximation, so that all bars appear almost parallel to the vertical axis. Thus, for any edge E of the approximation and given region B, we compute the edge index EI by projecting the region onto the edge, computing the standard deviation and scaling it with the relative length of the edge. The final barcode base is given by the maximum edge index. By the provided example, we have 6 edge indices, as to see in this image. Taking a closer look at the third and fifth projection, we see that the standard deviation over the projection results in similar values, but the scaling with the edge length that forms our final edge index shows a clear result. With the calculated barcode basis, we can then finally determine the final contour, which is limited to a rectangle and only enclose the visible area of the barcode. We start from the barcode base and select the shortest neighboring side as given and shorten the opposite one to the corresponding length. So, for the decoding library, like the zebra crossing, we use the and the barcode must be horizontally aligned. With the calculated barcode base, we can do this easily. But if the resolution of the barcode is too small and, for example, the image quality too poor, a direct decoding is not possible. In this case, we try to restore the image. For our deblurring module, we again use the unit architecture. So we consider the deblurring of a barcode as a segmentation task. We modify the model again to work with one channel input and reduce the number of filters by a factor of 8. The precondition for the deblurring module to work is a specific size and shape of the barcode. As you can see in this figure, we have set the barcode to a rectangle of 246 pixels times 94. The width of 246 pixels is due to the requirement that the thinnest barcode line should be at least 2 pixels. And the height is just set to the value. As you can see in the second row of the figure, after the rectification and the blurring of the barcode, it can be decoded. So, we know now that we have 3 networks in total for which we need a bunch of training data. And we created this data in a totally artificial way. The air label means the label in air shipment has a specific shape for which we create a simple template, as to see in this localization part on the left. On the right, we see an artificial generated image of the YOLO training dataset. As main background, we use images showing an empty loading area of a truck. For the representation of the shipment goods, we prepare a set of photos depicting stuff like wooden, carton, or plastic boxes. The generated labels are then randomly placed over the goods representation using a homography transformation. The generation of the learning data set for the segmenter can be easily done with the same method. We just crop the barcode area of the generated label, converted it to gray, and scale it non-uniformly to the size of 256 square, as to see in the right in the section of segmentation. And the green overlay indicates the segmentation mask. As our Deblurring module is a unit architecture, the learn dataset for it need also be a pair of input image and mask, as to see in the bottom row. For the randomly generated barcodes, we'll first apply some homography transformation, like randomly moving the edges with an offset between 0 and 5 pixels, which should simulate the inaccuracy of real barcode contour estimation, and add finally some noise and blur to the image. In order to test the performance of our approach, we create a new dataset. The array build, short AVB dataset, contains 400 images with a resolution of 12.4 megapixels each. The images contains 840 barcodes in total with certain different barcodes. The size of the barcodes varies greatly. The base length varies from 63 to 346 pixels. For each visible barcode, a polygonal mask with the corresponding barcode has been created, and yes, this data set is freely available and can be accessed via the given link. In order to explain the dataset a little more, we first examine how many barcodes can we recognize directly. As I already mentioned before, the requirement for the decoding of a barcode is its horizontal orientation. Since we have the hand-made polygonal mask for each barcode, we can easily align the barcode to the longest edge. We can see the results in the first row of this table. As you can see, the barcodes in the example image are very small. The shortest space is about 114 pixels. And the images are a bit blurry and we have bad light conditions. So none of the 4 barcodes can be decoded directly, and seeing over the whole dataset, not even 1% of the barcodes can be decoded in this way. So the second row shows the results if we warp the barcodes using the manually created mask and then deblur it. In this case, all barcodes, like in the example image, can be decoded correctly. And if we apply this to our whole dataset, the decoding of more than 55% is possible. The third row shows the results of warping and deblurring when we switch our segmentation on. That means we simulate the YOLO detection box by expanding the handmade mask by nearly 13%, creating an enclosing bounding box and cropping the barcode based on it. This row shows that our segmentation and contour determining module works very well. In example image, all barcodes can still be decoded, and in relation to the entire dataset, we have only a loss of less than 3% compared to the manually created mask. The last row shows the result for our complete approach. That means if we also use the localizer, you can see that for the example image, the decoding of the smallest barcode fails. You can see that the barcode is only partly in the cutout and that the contour was not determined correctly. Related to the whole dataset, we get a recall of over 45%. This is a very good result, especially since the localizer is a very easy to replace component. So in this table, we see the processing time subdivided on the individual modules. We see that most of the time, about 6 milliseconds, is due to the localization with YOLO. And this processing time is only executed once per frame. The segmentation and contour estimation and decoding with deblurring both take about 2.5 milliseconds. These times are about the same since both modules include the execution of the unit architecture. The module orientation and contour refinement is the fastest one and takes only 0.3 milliseconds. The execution time for the last 3 modules is per barcode. Considering a scenario like the one in the example picture, where we have 4 barcodes, we get a processing time of less than 28 milliseconds per frame, and thus can reach a considerable real-time potential. So we reached the end of this presentation. Thank you for your attention.